Welcome back to this channel, Feed Technology with me, Dito. Uh, in this tutorial, I'm going to show you how to ductile damage model in Abaqus. It has been usually used for modeling metals, damage in metals or damage in polymers, but it was actually originally developed for metals. But of course, it can be used for polymers as long as you fit correct parameters. So this is the plan of the tutorial that we are going to make. We are going to make a simple model like this. Yeah. The size will be around 100. The width will be around 30, and this will be 50, and the depth will be around 2 millimeter, all millimeter, millimeter, millimeter. Okay, so then this is the material parameters. I assume this is the material parameters for polypropylene polymer dummy stress strain curve. For simplification, you can put your own value if you have your own values for the stress strain curves. Okay, and this is the ductile damage should be explained later. Let's start. Yeah, first what we need to do is to create the model using 3D modeling space, deformable, solid. We're going extrusion. What you're going to do is first to create a I will make sure. Wait, I will make an additional line just for helping us later. Uh, this be 50, all right, and then the size will be 60. This distance to this distance, horizontal 60, 0. Then also this guy to this guy, also 60, and the radius will be 50. Then I'm going to get it a bit difficult. Basically, size will be 30, 0, and the height 100. Maybe you get confused now what I'm doing. But let's just see it. To move it, translate this guy. This done. Then from that location, 0. This is the first one. Then I will from this minus 50. So to shift to the left, and then 50 to the bottom. But why everything translated? Don't want everything translated. Select section, move again. this, okay, this to comma 0, okay, and then want to move again, this, 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 comma 0, minus e. They are moving. Something I don't understand. Oh, mistake here. Okay, so I need to delete this guy because it's supposed to be here from this guy to here. 60. Am I right? And then this should be 30 cents. So this guy should be 55. 5. Yeah, right. Okay. Change this guy 45. Sorry guys if it's a little bit difficult for you to follow. Basically, you want to make this a little bit like narrow here, narrow in the middle. Choose this trim, auto trim. Just remove this guy. Okay, nice. It's good. Be good, right? Then close it. Section must be closed for this type of feature. It's closed, right? Get it why it's not closed. We're using section must be closed. Don't know what to do now. Oh no. Easy. Let's just make it here. Let's auto trim again. Sometimes things are not working as planned. Need to get creative. And I will make a symmetric. So it's good for you guys if I make a mistake. Means that you learn new things from me. How to make it like projection, like you know what I mean, symmetric. I want to like the symmetric here. I remember there is yeah here pick the mirror line. This is mirror line. Done. Select the mirror entity. Select this 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 this. Click done. Mirror now. Then I can delete this middle part. Trim. Same thing. Done. That will be 2. Nice. This is the model. So to make sure we have a good model, I need to partition and click here. Partition cell. Find cutting plane. Like 3 points. So select 3 points that will cut the cell. We'll cut 1, 2, 3. Partition. Cut them that. Okay. Same with this guy. Okay. Points. 2, 3. Partition. Done. see it's nice now. And then that's it. Property, get material property with elasticity, young modulus 1700, 0.4, like the one I put it here. And MPa, the elasticity 20, 0, 25.1, 34, 3, 31.5, right? Right? 3.5, yes, makes sense, right? Make sure, okay, guys, just a reminder when you copy stress strain data from an Excel of an experimental data, usually your plastic strain is the one on the left, yield stress is the one on the right. Here, your yield stress here, your plastic strain here. So you make sure that you put the correct data in that columns, okay? Those columns. Then for damage, here, damage for ductile metals. It's actually originally developed for metals, but still you can use it for polymers if you want. Ductile damage, fracture strain. So let me explain a little bit. What's the meaning of that? So if we plot these stress strain curve, sigma yield with respect to epsilon from experiment, not sigma yield, it's a sigma. Have the stress strain curve. Yes, comes down. Say we just plot till now. So if we are at this point, and then we unload, assuming elasticity, here is the plastic strain. From here to here is the elastic strain, while here from here to here is the total strain, epsilon t. So fracture strain here, basically, when you saw this curve, and then, for example, this curve tells you 0.3, the value here is not 0.3. What the Abaqus wants is actually, when they say fracture strain, is not this total strain from this maximum point. What he wants is actually the plastic part of it. So in this case, the fracture strain that we're going to use is somewhere around 0.0.5, like 5%. Make sure fracture strain here is only the plastic part. The stress reaxiality, explain a bit. When you do a tensile test, for example, like this, you get the data. Your reaxiality is around -1.3. Yeah. How to calculate this? Reaxiality or eta is equals minus P over Q. If you're doing a tensile test, your stress tensor A 0.0000000. In this case, A is the stress in one direction, while for other direction, stresses are zero because you are doing uniaxial tensile test. So you will only have one components of stress that is non-zero, while other are zero. Okay. So if you calculate the P here, P is sigma 11, sigma 22, sigma 33 divided by 3 with minus, I think. So in this case, your P is minus A 3, not minus, I think. While the Q here is basically the von Mises stress, which is in this case your Q is equals to A. So when you calculate the traxility over Q minus, will give you minus A over 3 divided A, which is actually minus 1 over 3. So if you get the stress strain curve from uniaxial tensile test, this value will be 0.33. Strain rate, assuming this is non-strain rate dependent, or you test at a very low strain rate, just put the value of 0, that's enough. Then for the damage evolution, here we need to get the displacement at failure. So what is the displacement at failure? So if I come back to this point, as I said before, is the fracture initiation strain, which is this guy. And then this guy will freeze, right? Or maybe like this, or maybe like this. The slope of how fast this curve is going down is now defined by these damage evolution parameters. Here you need to put displacement at failure. So what is that displacement at failure? So when you're doing a damage modeling, in this modeling, exactly the one that we are using right now, they will have this failure displacement, which is actually plastic strain effective times the length of elements. So if for example, in this video, I will use the length of element. This is the characteristic length of elements. I will mesh my model with 1 millimeter length, and this guy, imagine from here, the strain is 100%. Just imagine 100%. It really depends from your experiments. If you want to have a more brittle, you can put 0.1%, 1%, 10%. It's up to you. In this case, I assume this is 100%. So the delta F will equals 1 millimeter. Okay. So value now, I'm going to use millimeter. So imagine now I want to make a brittle behavior. It's very short. I will not use 100%, maybe only 10%. In this case, uh, this one will be 0.1 times 1, and then will become 0.1. So I should change this guy 0.1. So it really depends on how brittle your materials. You need to do calibration testing these parameters to match your stress strain curve. But for now, I'm going to stick with this one. Okay. Okay. Then grid solid homogeneous, continue, and then I'll click here, science section, click everything. Nice, done. Assembly. Okay. Step for step, I will static general usual. As usual, I will click geometry and put some dissipated energy because this is a simulation with damage. Sometimes it's really difficult to converge. And make sure you increase the number of maximum increments, maximum number of increment, because sometimes it takes more than the default 100 increments because you need to solve damage problems. Okay, click OK, and then as usual, like in the adhesive element formulation, you need to change also this general solution control to make sure that the abacus will do iteration as much as they can, because the default iteration number that abacus allowed is so low, around 4 and 8. Abacus doing simulation, there are so many parameters in mind. These are the parameters for the looping for the iteration. So if by default, if the iteration done 5 times and still not converged, they will show error. And then this method before, I just change it to 20, I think, right? 20. So I enforce them to iterate more because I know that my problem is more difficult to converge because I include damage. And now I'm going to check SDEC. SDEC is for the damage evolution law. And there is a damage criteria. This one, damage initiation criteria. And this is as usual, intervals. And this is the history output. I will make the same 100 intervals, 100 frames. Okay, something I'm not sure. Maybe just click here. Sure it will work. Uh, now step already done. Interaction, no interaction, load. For the load, I will just simply okay, make everything here. We'll pull in the uh, I will make the U2 direction right. It's 10 millimeter. I pull 10 millimeters up. Okay, and then the mesh. Gate it. Just okay. So I use 1 millimeter, right? Because if when I select the parameters for the damage, my characteristic length was considered as 1 millimeter. So I'm using 1 millimeter, of course, there because of this non-uniform geometry, but it's good enough, good approximation. Yeah, so you guys need to make sure that the size is uh, has a very good aspect ratio around 1 to make a good simulation using the damage, the ductile damage. And then we click this guy and second order accuracy. Want to make sure that we enhance hourglass, so there's too much hourglass. Element dilation, yes. Maximum degradation. When you're doing damage for, for stress, 1 minus d sigma 0. Sigma is the k0 times this is the stiffness matrix, this is the strain tensor. Okay, so when d equals 1, when d equals 1, usually it means that it's fully damaged. But of course, in reality, in practicality, you don't want d to be close to 1. Why? Because in some cases, when you want to calculate sigma 0, you need to do this version, and then when it's d equals to 1, we'll divide this by 0, infinite. So what people do usually in their code, they will limit d somewhere around 0.999, a small value, but it's already damaged. But in this case, it will not cause this infinite problems. Yeah. Okay. And now what we need to do is to submit the job, create it, parallelization. We're using 4. And I click submit. See, oh, there's no problem if it's running or not. And when it's running, I will just pause my video first. It's gonna take some time. But I want you guys to click monitor so you guys can check, can see later when you started it, the time increment will be around 0.01. But when the convergence problems start to occur, it will it the time increment will get smaller because they want to simulate this rapid damage propagation. Okay, working now? I don't know. Let me pause. As you can see here, guys, it started from 0.001 because this is the initial value, and it get faster, faster, and now this is the maximum value. Why the maximum value is 0.01? Because the total time period that we use in the step is 1 second. Then we enforce Abaqus to export the field output 100 intervals. So it means that Abaqus needs to stop at maximum 1 divided by 100, which is 0.01 seconds. So this is the maximum that Abaqus can jump in their time increment. Otherwise, they will not be able to write field output at that specific time, because we specified that we want 100 interval, 100 frames for our field output. So now it's good. I'll pause again the video and then show you once it's done. All right, guys, I'll come back again. It's still running. You see the monitor still for 43% of the total simulation, because the total time is 1 right now. It's 0.443, it means 3%. But I'm sure we can already get the results so far. Okay, this is the stress. Oh yeah, this is the stress. We check the ductile criteria so that all of this area has been close to damage or starting to damage. This is the damage value as DEG. So in this area, the damage already 0.7. It's almost fully fractured. Fully fractured means 0.999, as we said before, because it cannot reach 1. Huh? Maximum that we allow is 0.99 to make sure that there is no convergence problem or division by 0 in our simulations. Yeah, you can just wait for the simulation, but this is the idea. So let's now, simulation is going to take time until it's fully fractured, guys. So I will not wait until the end, but I am sure you guys understand now how to do the simulations. And 28 minutes. So before I stop this, I want to do data processing, because this is something that I haven't done. I want to see already fully fractured, guys. See, when this material is fractured, it doesn't mean that the material is removed from the equations. The material is still there. When you're using Abaqus standard, the Abaqus never remove the material physically from the equations. So what Abaqus standard did is just basically not displaying the materials, okay? So the material is still there, but you cannot see it. How do we, material still in the equations? How do I know? It's from the manual. It's totally different with the Abaqus explicit. When you're using the Abaqus explicit, they really taken out the materials, but not with the Abaqus standard. Okay, so if you want to calculate the reaction force, this is what you need to do. ODB, field output. Going to choose this unique nodal, RF, RF what? RF2. Yeah, is it RF2? Yes, in the Y directions. Nodes, choose edit, not individual but by angle. Okay, done. 93 nodes. Okay, and save and dismiss. Click here, just all of them. So what I need to do is to sum all these nodes. Create, operate on XY data. Sum, press sum here, right? But simply type sum, double bracket and bracket. Come back again here, and then break down, then press shift and click, add to expression, and save as sum. You can just put any name. So it's some, then yeah, want to plot it. Yeah, this is direction force. So if I want, just reverse it. So I minus the sum. The data I need. As you can see here, there is this linear elastic regime. This is the plasticity, and then the damage start to decay, right? So that's all for our tutorial today. So as I said before, I want to control this area. Uh, Explain a little bit about this curve. Okay, we are so slow, guys. Okay, so this area here is defined by E, which is in this case 1700. Okay, then this area here is defined by the sigma yield versus epsilon P, which in this case I choose 20, 0, 25, 0.1, and so on. And this area here is basically the slope is defined by this d delta f, effective plastic displacement, the value of 1. If you want, for example, to make it a very sharp jump like this, you use 0.1, depends on what you need. Okay, and I hope this video is clear enough for you guys and very useful for you. Please don't forget to subscribe and check my Google Scholars and cite my papers. Check my Google Scholars. So cite my papers as you need. Some material data are there. You feel free to check. And goodbye, everyone. Thank you.